Hope you enjoyed your lunch. Yeah, I apologize for 2 buzzwords in the title of this talk. But this actually makes sense. I will explain why. If you remember Industrial Revolution, when machines helped us to build better machines, then our digital revolution, web revolution, when our computer programs helped us to build better computer programs. And the same analogy here that, okay, we're building AI, and actually we started using machine learning methods, techniques to help us building better AI. You're probably aware about some automated feature engineering efforts, about meta learning and other cool stuff. And today in particular, I want to focus on monitoring aspects, monitoring of machine learning models after they have been deployed to, in production. Yeah, very short credits to this talk. This talk is based on our open source efforts, and this is the team which contributes, main contributors to this project, the Hydrosphere.io. So let's jump straight to the details. So once the machine learning model has been built and it is deployed to production, what might be wrong there? So these are just a very brief list of the possible reasons, possible failures that may happen in production, and you are probably aware about that. So the main thing is discrepancy between training data and production data, and other stuff that is listed here. And one of the best practices or recipes for providing observability and reliability of machine learning models in production is to use data contracts. Data contracts means protobuf contracts that describe the inputs and outputs of your model. So you will solidify basically the contracting space of machine learning models, and you will be automatically validating all the messages that is to be sent to the model in online, in real time, in production. The data profiling, data profiling, concept drift monitoring, it's probably the similar terms. I will explain in details in this presentation, this talk in more details. And I will skip the other to smart subsampling and active retraining, because the talk is for 20 minutes. Just a little bit theory behind this. So the model has been trained on original data set. Imagine your model has been trained on an original data set, and you've trained a classifier that can classify between orange circles and green squares. That's great. This is the concept that your model has been learned. And actually, that blank space here, besides the orange circles and green squares, is a blind blank space that your model has never seen before. And this is, I call it uncertainty. Just because we are not sure what is the real world outside of these boundaries. What may happen in these boundaries? So there might be a gradient edge cases between two classes we have learned so far. There might be a new concept in production. So we might discover a new type of traffic signal, for example. That we have never seen before, and we should monitor our traffic to discover those new concepts. The user behavior, the system behavior, the world behavior is being changed over time, and the concept might be drifted. So then, given that, so let's recall how the data science and machine learning process starts and what's the common workflow on a very high level. So the data scientist makes some assumptions based on the results of data exploration. Basically, he engineers features and he makes those assumptions. And once the model has been pushed to production, it works if and only if the format and statistical properties of production data are the same as in research. I think that's obvious for everybody, and the whole framework is clear. So that means that in production we have to continuously do a data profiling and verification, comparing it with the data profile of our training data sets. Let's take a look how the servable and deployable model might look like. So it's not just a binary protobuf file saved if you're familiar with TensorFlow. It's not just a protobuf model with coefficients saved to the disk. It's much more. It's wrapped with all the infrastructure stuff. And one piece I want to pay your attention to is that red cube. That the deployable and servable model has to be packaged with training data statistics that might be like min, max, range, and other statistical properties of the training data, and some more like derivatives like quantiles and autoencoders that represents statistical snapshots of the multi-dimensional data sets. So it guarantees us an immutable deployment of our machine learning models, because the machine learning model is tightly connected to the data that it has been trained with. And moreover, those once we version this servable model, the training data sets also have to be versioned in this way. So it's just a side note, but let's see. I want to show you just interrupt with slides and just want to show you how we basically designed this deployment component and how we package the training data stats into that servable model to be monitored and to be validated with later. So we have. So this is. Can you see it well? Okay. So we let's see what's here. This is basically a folder when we have the model. The model is being just a simple Python model in this src file. And how we describe these, we describe the deployment mode for this is serving YAML here, and those are contracts. Don't pay much attention on this, but I wanted to highlight this thing. So it's a reference to the training CSV. So the training data that it comes with the model itself to be packaged and deployed in immutable way there. And once we get HS upload, we package it all together and send to the serving cluster. And during this process, you see the data profile computing is started with something. So what we do, we take this training data set and we start calculating all kind of statistics on this, like mean, max, quantiles, and whatever. And also we calculate such things like autoencoders, for example, that represent the more powerful statistical snapshot of the multidimensional data. Yeah, it takes some time. Yeah, it's finished just for the sake of this. And the training data itself, I will just show you. It's just for the sake of this presentation. It's just a CSV file with feature vectors. It's like 112 feature vectors of the profile of the client profile. And once it's deployed, so yeah, so this new version has been just uploaded and deployed. I will just, we have the data profile here that has been calculated. So what happened under the hood? These like common statistic, quantile statistics, and descriptive statistics has been built, and the histograms. That's cool. We know something about our training data. What happens next? In production, we can simulate. Right now we can simulate like sending a prediction request to this model, and see how those prediction requests are statistically different from the training data we have seen so far. I've done that before my presentation has started, and but it just pointed to another model version we have here, and yeah, we gather some statistics here, and we apply some statistical checks like Kolmogorov-Smirnov test, and so on. And what we do is, I just picked up the different model version that has been. You see, we have some insights that there is a training data and there is production data. Distribution has been changed, and we can make a decision out of it. We can make provide an insight or alert to the machine learning engineer. Okay, if something is going wrong, you might be maybe upstream pipeline has failed and start sending you like zeros instead of expected data to be used for the predictions. This is cool. This is already like step ahead towards more observable machine learning models in production. But let's move further. So this is like a very basic first step that we can do. This is the same. So imagine we have like 100 features as an input, and every feature generates 20 profile metrics to be watched. And it means like 2,000 points to track on every input request. So it's kind of impossible to sit and watch those metrics and figure out, okay, my mean value of a particular feature number 97 has been changed. And what does it mean? It means nothing for me. Yeah. So too much data to track. We can squeeze this points to track into using some well-known advanced statistical methods like Kolmogorov-Smirnov test, as I mentioned, quantiles plot, or PCA, or principal component analytics. So this will give us a more holistic view of what's going on without like digging into every particular every particular feature and its statistics. So, but this is not like this is like one layer ahead. Then the next challenge. So if we imagine we have trained image classification model, and once it has been trained on monkeys with black faces, and what would happen with our system if in production we will all of a sudden have we'll start receiving monkeys with red faces? How can we map this this like fact into the concept I have just described with that new with that plot? Because like the image is it has like the 300 on 300 and 3 multi-dimensional vector. When we start talking about the outliers detections and the analytics of the image data and anomaly detection in general, so the first model that we have in mind is like autoencoders. Classical autoencoders, they have encoder that basically engineers features for you, and decoder that tries to reconstruct the original image from those features or intermediate representation. And basically, reconstruction error means the level of anomaly of new image. So if we trained our autoencoder on our training data and then score this in parallel with the main model, we can have a kind of insight what kind of anomaly we have in production. This is good, but the challenge is we have just red or false or true flag that it might be an anomaly. We don't have, we can't estimate a probability distribution of this intermediate representation. So this is we can't dig deeper into the root cause analysis here. There are another methods you can there are another methods like GANs you've probably seen. We can use GANs as well for this concept drift detection, and basically if you remember, GANs can distinguish between fake and real images in a classical and a canonical scenario. In this case, we train GANs to learn this uncertain space. So we this like black curve is something that GAN is aware about, and if our prediction hits into this black curve, we can say, okay, this is something like drifted towards. So the same. We can use like discriminator, and output of the discriminator might be like drift or fake data or good data. Also, don't have any explicit insights on actual probability distribution of this latent space. I will just skip through others, but okay, there are other many methods are currently in the bleeding edge research, like variational autoencoders, when we can apply a certain constraint on our training algorithm and learn this latent space probability distribution. So we can figure out what's going on inside these features. Masked autoencoder for density estimations also would skip it, and like globe bidirectional GANs. At the end of the day, very simple. All those methods try to build a histogram of your training data and histogram of your production data, and you can like figure out what's the difference. Yeah. We've been using those like combination of those methods to build a promising. It's in a proof of concept mode at this moment. I would show you a video, but I don't have like a real-time demo. So what we've done so far, so we've trained our original single-shot detector model on a Berkeley dataset. So it trained to recognize traffic lights, pedestrians, cars from Berkeley. And then we have deployed this model in a little bit different urban area, and then deployed our like monitoring models in parallel to analyze. Okay, is there any difference in this like new urban area from the original Berkeley dataset we have seen so far? Yeah, and the traffic lights here. So you see, we can like understand that this particular traffic light is hard to. We have never seen this type of traffic lights before, and we can convert it into actionable metric or alert to be used for future root cause analysis here. And if you will dig deeper into the real why these like traffic lights are so hard to be recognized, these like green errors are hard to be reconstructed. So you see it is being reconstructed into the like a circle. In this case, yeah, mostly in star. So the additional black arrow, green arrow section that has been added into the side of that traffic light that caused such a that it hit that uncertain blank space of the model, and yeah, ability to detect it using other machine learning models that works like in offline, not in offline, it works in asynchronously in parallel and analyzing this traffic is like a big deal for providing insights for data scientists. Yeah, in the future, of course, we can use, we can add this. It might be outlier, it might be a new concept, it might be something like these scenarios might be different. We can add those outliers to the next SAP sample, to the next retraining and relabeling workflow, and train our models to be aware of these concepts we have discovered in production. So this is like the idea is to provide that hook in production and help us to like iterate further and further. Yeah, I think I'm done with the talk. I'm happy to take questions.
Thanks, Stepan. Questions?
You say you're going to take the outlier and provide it as a hook to the model. How do you intend to do that?
The intent not to provide the outlier to the model, it provides the data set that has an outlier to the next retraining batch. So we can retrain our model to be aware of those outliers. Or it might be not an outlier, so it's originally it's like anomaly detection stuff, but as I mentioned, there might be like there is a new concept, yeah. So it's not an outlier. This is something that we should work with. We could not. Usually, when people talk about outliers, we usually filter outliers, yeah. Just not to deal with them. We don't want to deal with outliers. But here I would say, today it's an outlier. Tomorrow it's a new cluster of your data that you have to be aware of.
Do you have a measure of severity of, let's say, how production data are different from the original training data?
The
single number.
No, we don't have. So we can from the statistical stuff that I have showed. Yeah, we can derive that just a difference between histograms and have just that one number. For this one, it's probably a combination of different metrics and monitoring alerts. So we don't have a. And one single number may not be explainable. That's why we would like to. Okay, of course we would like to have here, for example, when we say, okay, it's a health. It's ideally on the top of every model we have like a red and green health status. But then we want to dig deeper into. Okay, the root cause and so on and so on. Yeah, and this one is an example of GANs. And if I would start sending outliers there, it will be all red. Yeah. Yeah.
Just to rephrase this question, I think it was interesting to me. What is the threshold for you to set the status to red rather than green? Do you have a threshold?
Yeah, every metric we want to apply for this type of, for every kind of model has its own like threshold. The threshold might be learned automatically from the training data, or it might be set up manually if you have some insights or you have some like guess about the training the production data you can expect. For example, yeah, but you know it's there are if we talk about statistical properties, yeah, you have 20 properties: mean, max, average, and so on. and if you have like 100 features, it's impossible to manually curate all those metrics. That's why we want to like automate this stuff.
I see.
Yeah.
Thanks. So, thanks again, Stepan.
Cool.